That's
Okay.
good.
All right. So, yeah, thank you again, Bruce, for I know it's you're just in your office, but it's big for us to have you come in and give a talk. So I really appreciate it. Um, is there any other things that we want to say at the top, Andrea or Mike?
Nope, all good.
I think
Nope,
we're
I think
good.
we're ready
So
to go.
yeah, so Bruce, I'll hand it off to you. Thank you again.
Great, thank you. And thank you for the invitation. I'm truly delighted to be able to give this talk. It's one I've been wanting to put together for a while, and I hope it'll be interesting. I've been watching people join in, and I see a few Mars experts who I didn't necessarily expect to be here. So to those of you who may know more about some of the things I'm talking about than I do, if I say anything that is at all misleading or incorrect, please feel free to just keep it to yourself. What I'd like to do is, well, Michael invited me to come and talk about a recent paper on the future of the Mars climate as the sun heats up. But in order to do that, I've got to go into a lot of context and background. So really what I'm going to talk about is the past, present, and future of water and climate on Mars and what that might say about possible life. I think everybody here knows that climate and life are the overarching questions for Mars, trying to understand what the history of climate has been, why Mars made a transition from an early, what appears to be a warmer and wetter environment to the cold and dry environment we see today. Whether there's ever been life on Mars in the past when water might have been more abundant at the surface or at the present, perhaps buried under the surface or in tiny trace amounts of water, liquid water that might be present. And then what's the future of the climate going to be as the sun heats up? And can we terraform Mars? It's hard to talk about the future climate without talking about that. I'm going to start with the basics since I know some of the people here may not be as familiar with Mars. Mars is about half the size of the Earth. It's about half again farther away from the sun than the Earth is. And despite having a CO2 atmosphere, the greenhouse warming isn't great enough to allow any significant liquid water at the present. That doesn't mean it can't occur, but it seems to be very trace in abundance. And just to be clear, Mars here is the one on the right, Earth is the one on the left. And this is my attempt as best as possible to show them at their relative sizes. Mars is about half the size, half the diameter of the Earth. Today, Mars is a cold and dry planet. We don't see conditions that would allow liquid water to exist. We see a lot of evidence for wind-blown material, for temperatures that average maybe 50 degrees C below the freezing point of water. That would be at the equator, and at the poles even colder. Despite that, we do see water present on the planet. We see trace amounts of water in the atmosphere. I picked this picture to show it just because it has clouds that are water ice. You can see the polar ice caps up at the North Polar Cap up at the top of the image, giving you a sense of the scale of it. If we look at the weather today, it's driven largely by the presence of airborne dust. And we see dust in multiple forms. The global dust storms off on the far right that can cover the whole planet, local dust storms that can be hundreds of kilometers across, all the way down to dust devils that are sub-kilometer in horizontal scale and several kilometers in vertical scale. These affect the weather mainly by absorbing sunlight and emitting infrared energy and dominating the control of the temperatures and thereby the dynamics of the atmosphere. This is different from the Earth, where it's the presence of water that really dominates the energetics of the atmosphere, water and clouds. These dust effects are not unfamiliar to us. We see the same things on Earth: dust devils, local dust storms, and large-scale dust storms. We don't have the global scale dust storms that Mars has, because water can precipitate and rain the dust out of the atmosphere before it can get carried globally. I showed this one just because this picture of Phoenix in the middle is truly amazing, seeing a local dust storm like that. We do see water ice frozen in the polar caps. Here's several different scales. We see layering in the ice that suggests climate change. And we see in the middle image, these arcuate forms that suggest some sort of movement or connection to dynamics of the atmosphere. We also see ice in mid-latitudes in deposits that are buried beneath the surface. And to give you a sense of this image, we're looking pretty much straight down. At the top, we're seeing a flat plane. That sharp line about a third of the way down marks the start of a scarp. And then if you're moving toward the bottom, you're falling down the scarp. And about 2/3 of the way down, you hit the bottom. The ice has been very cleverly colored by somebody to be blue, because everybody always likes to color water and related features blue, but it shows you the extent of that. It's a deposit hundreds of meters thick that contains a significant amount of water. Despite the cold, dry environment today, there's clear evidence for water having been present in earlier times. In this image, you see the branching tributary systems analogous to water runoff on the Earth, where small channels coalesce moving toward the bottom of the image to create larger channels. These are termed valley networks in order to keep the description of it separate from the physical mechanism, but it sure looks like runoff of liquid water. The abundant impact craters tell us that these occurred early in history, up to about 3.5 billion years ago. So something changed in either the availability of water or the climate to go from an environment in which these could form to one in which they don't form. We also see catastrophic flood channels. The scale bar here, note that's 100 kilometers. The water is flowing from left to right through this channel. You can see teardrop-shaped islands. I'm going to see if I can bring up a laser pointer here on the screen. Can you see the laser pointer now?
Yeah.
Yes.
Great. So you can see teardrop-shaped islands here where an impact crater served as a barrier and water flowed around it. These islands created by the flowing water. And just to give you a sense of scale, the width of this is more than 100 kilometers. So think of this as analogous to the Mississippi in flood stage. We're going to come back to these in a few minutes. From the Curiosity landing site, we see mudstones within an impact crater that was thought to have contained a crater lake at one time. And if you map out composition of minerals, you can identify a lot of minerals that really require liquid water to form. Most of the dots here represent one form or another of a mineral that requires liquid water. In particular, the blue dots are phyllosilicates, which really require liquid water to have formed. These are minerals that are exposed now at the surface, but are thought to have formed beneath the surface. So it suggests that there's been liquid water flowing through the rock beneath the surface. Okay, now we get into the guts of this, because that abundant evidence for liquid water earlier in history flies in the face of the fact that the sun was 30% dimmer earlier in history than it is today. So we require greenhouse gases to have been present. Models have been put together for the last 20 or 30 years trying to explain the greenhouse gas that would be necessary to raise the temperature, and they haven't succeeded yet. For example, 4 billion years ago, the sun was 30% dimmer. As you add CO2, you don't raise the temperature up to a warm enough temperature. So people are putting other gases like hydrogen gas into the atmosphere and then trying to understand how they could form. All of the models, though, really require CO2 as a base greenhouse gas. So we think there must have been a lot more CO2 early on than there is today in the atmosphere, perhaps 1 to several bars of CO2. That really begs the question, where did the water go? Where did the CO2 go? And getting back to the topic that Michael asked me to address of the future, we have to understand what the availability of water and CO2 is today to know where it might come from. And that really requires asking what happened over the last 4 billion years to remove gases from the atmosphere. If we're going to do this, we really need to look at Mars as a complex system of coupled components. I've tried to represent here the different components going from the deep interior, including the mantle and juvenile outgassing, shallow crustal reservoirs, the shallow regolith, up to the atmosphere, which is what we see today predominantly, but then the upper atmosphere and the ability of different mechanisms to remove gas from the atmosphere to space. If we're going to track the history of water and CO2, we need to consider each component, how they couple together, and how different components result in supply of gas or loss of gas to or from the atmosphere. And I realize I've left one out, even though this is a nice brand new chart, and that is impact supply of gas to the atmosphere, especially early on during the tail end of accretion, as asteroids and meteorites bring volatiles in. So I want to start with the known sinks for carbon dioxide. And we're going to go through this for water and CO2. I'm not going to go into the details of each process in any significant detail, but I want to talk a little bit about them. I'm going to start with the second one on in the chart here, and that's the stripping of gas to space. And I want to start with that one because it couples to the MAVEN mission, which I've been involved in, and is one of the more important mechanisms of losing CO2. CO2 can be lost through photochemical processes. If you're familiar with the term dissociative recombination, that can break apart a CO2 molecule and give the individual atoms enough energy to escape. It can also be sputtered away, where ions in the upper atmosphere can be picked up by the solar wind and slammed into the atmosphere at high velocity and kick stuff out. Based on the isotopic evidence, that is the ratio of carbon 13 to 12, I think that has removed between about 1 and 2 bars of CO2 through time. That is a significant amount of CO2 if you think about how much gas might have been serving as a greenhouse gas early on. The first line on here is impact ejection to space. During the tail end of accretion in particular, or during a late heavy bombardment phase, impacts can come through the atmosphere and knock gas out. They may have removed as much as a half a bar to a bar of CO2, but it's really hard to quantify. Stripping to space is also hard to quantify because for these to operate, they need to have gas in the atmosphere. You don't eject much atmosphere to space if the gas is not in the atmosphere. Moving down, there's some CO2 that has been identified as ice within the polar caps. That can contribute about 6 millibars. There may be a CO2 water ice clathrate that could contain as much as 30 millibars of CO2. It hasn't, no clathrate has been identified, so this is a theoretical limit. In terms of carbonates, this for a long time was thought to be a major sink for CO2, but no large deposits of carbonates have been identified. Stuff that is near the surface and has been exposed, if you add it up, it would be the equivalent of like 14 millibars of CO2. Adsorbed gas, where CO2 molecules can just attach themselves through a light bonding to grains of the regolith. This depends on how much regolith there is. I won't get into it here, but I will later. I think there's about 35 millibars. of CO2 available there. The biggest uncertainty is carbonates that might be present in the deep crust. Some have been identified where they've been exposed either tectonically or through impacts. And if the amount that is visible is all that's there, that could be as little as 10 millibars. If it represents a global layer buried 5 to 10 kilometers down, it can be as much as a bar of CO2. If you add all these up, just taking the numbers, it's between 1.5 and 3 bars, or this uncertainty on deep crustal carbonates could mean it's a lot more. This is enough to be consistent with the amount necessary to produce that base layer of greenhouse warming, but it's probably not going to allow liquid water. So we still need something else as a greenhouse gas, but the CO2 seems to have been present in amounts necessary to get it started. Let's move to the sinks for water. I'm going to start at the top with the present day exchangeable water. I've shown images of these, the water in the polar caps, the water present as ice in the mid-latitudes, that 100 meter thick layer present in mid-latitudes. If you add it all up, it's equivalent to a global layer 20 to 30 meters thick spread over the planet. This is the way we measure it. If you took all that water, put it at the surface in a uniform layer, how thick would it be? So that would be 20 to 30 meters. The amount of water lost to space can be estimated by the enrichment in the ratio of deuterium to hydrogen. The D to H ratio in water today is about 6 times terrestrial, 5 to 6 times terrestrial, and that requires loss of a significant amount of water to space. That's the most likely mechanism for enriching it. Hydrogen is lighter, it escapes more readily than deuterium, so water that is left behind is preferentially enriched in deuterium. There's an uncertainty, but my best estimate is between about 100 and 600 meters of water as a global equivalent layer. I showed you a map of water incorporated as water of hydration and minerals. My best estimate is 130 to 260 meters global equivalent layer. It could be more because there could be lots of stuff that we haven't seen that's still buried. Water that had been present in an early ocean and may still be present in the northern lowlands beneath the surface, based on some work by Carr and Head, that could be 100 meters or thereabouts. These add up to between about 400 and 1,000 meters of water. Now, there could be additional water buried as free water or ice within the crust that can be between about 300 and 1,000 meters global equivalent layer. So if you look at the full, and I'm going to talk about that in just a second. If you look at the full range, it's between about 400 and 2,000 meters global equivalent layer of water. First, this amount of water supports the geological requirements based on the minerals we see, the morphology, the valley networks, the catastrophic floods, etc. Second, we can put this in context by comparing it to the amount of water at the surface of the Earth. The water at the surface of the Earth is primarily the oceans, and it's nearly 4 kilometers thick as a global equivalent layer. If you scale that to Mars by the size of the planet, the mass and the size of the planet, it would be about 1,400 meters. So comparing that 1,400 to this 400 to 2,000, it appears that relative to the planet's mass and size, Mars has had about the same amount of water at the surface that the Earth does. There's no real underlying significance there. It just helps put it in perspective. So I want to talk about the inferred crustal water. I showed this image on the left already, water coming out of the catastrophic floods. Here's another image on the right that more clearly shows water appearing to come over at the right-hand side of the image from beneath the surface and then flow out over the surface. These catastrophic floods are not randomly distributed. They're located in one part of the planet. I put boxes around those two images from the previous chart, but you can see where water is flowing, released to the surface and flowing up to the north and then into the Chrysi Basin, the northern lowlands, and where Valles Marineris, this large canyon system, grades at the left end from being a tectonic feature over at the right end to being this flood feature, where all these things relate to flow of water also into the northern lowlands. When Michael Carr looked at this initially, he drew a circle around all of these water-related flood features and said that's about 10% of the planet that has been drained of water. He postulated that there could be water within the crust in the remaining 90% of the planet. And if there is, that would amount to up to a kilometer of water as a global equivalent layer. So the question remains, is there any free water remaining in the crust? And I've got to go through this discussion because when we get to the future of the water going forward in time, whether there's any water present in the crust is going to be important for how much water makes it to the surface. It's also an important issue because there was a paper last year by Wright et al. That claimed to identify water within the crust. And I picked this one chart off of their press release saying they found lots of water. If there is water filling the pore space in the crust, either as water, liquid water, or ice, and if it's in exchangeable contact with the surface, it would be the most important reservoir. So I want to examine their analysis in just a little bit of detail. What they did was to look at seismic data from the InSight mission, which included a seismometer, to see if that could constrain the amount of water. The seismic data can be used to derive the P wave velocity, S wave velocity, and bulk density of the crust. That was not done by these authors, but it's been done by a number of groups. What they did was to create a rock physics model to explain, to calculate these three parameters, P wave, S wave velocity, and bulk density, based on the mineral bulk modulus, shear modulus, bulk density, and then the porosity, the pore aspect ratio, and the liquid water saturation, which is how much of the pores are filled with water. And they looked to see what combinations of parameters might explain the seismic data. This is a figure taken from their paper. Look only at the black line. This is the probability distribution shown as a function of the liquid water saturation, going from no water at the left up to 1 filled with water at the right. They argued that this is a well-resolved peak, that it clearly points to values near 1 being the best explanation, and they concluded that that there was water in the crust and that it most likely filled the pore spaces. I disagree with that interpretation, and this is my attempt to look at it from a different perspective. The black histogram is the same curve as was in the previous chart, but when I look at it, it doesn't look like a well-resolved peak to me. It looks like any value from 0 to 100% water saturation is viable. The red curve is the cumulative distribution, just integrating the values in the black curve, going from 0 probability for 0% up to 100% probability for 100% water. And the vertical dashed lines represent dividing this into quartiles. So each one of those regions demarcated by the vertical dashed lines has an equal probability of having the value of the water in the crust be present. And when I look at this, I conclude that any value is plausible. High values are a little bit more likely than low values, a factor of 2 or so, but there's nothing to rule out between 0 and 36% water has the same probability as between 85 and 100% water. So my conclusion is there's really no information in the seismic data at this time about how much water is present in the crust. It could be anywhere between 0 and 2 kilometers global equivalent layer. It's really too bad because it would be nice to be able to constrain that. Okay, we've talked about the water from the past and the present. What about the future? This gets to the guts of what Michael originally asked me to talk about, and that is what's going to happen to Mars as the sun heats up over the next 6 billion years. And this figure shows the logic. The sun's going to heat up. Remarkably, Mars will heat up as well. That will release water and CO2 into the atmosphere. And could you end up with a nice Eden-like planet? This shows the same concept, but with a little bit more detail and how I want to investigate this. We're looking at the physical driver of the increasing solar luminosity. What's the Mars response as temperatures increase? What happens to the CO2 and water? And how much is going to be released to the surface? And then depending on what happens subsequently, do we end up with a wet CO2-rich planet, or can the CO2 form carbonates, water, hydrate minerals, or escape, and we end up with a planet that is just as dry as we have today? So I'm going to work through these a little bit. The figure on the left shows a recent model of the solar luminosity as a function of time. That's the solid line, going from about 75% a few billion years ago, 75% of its current value. Remarkably, it has 100% of its current value today, and then increasing up until about the time that we go into a red giant phase. When we hit red giant, this goes up very dramatically, and ain't nothing going to survive on Earth or Mars. But let's look at it during this interim period up to about twice the sun's luminosity. I've taken the simplest approach of using a zero-dimensional energy balance calculation to calculate global average temperatures. And the numbers are covered up on my screen. But if you look at the numbers in the red oval, they're all up around the melting point of ice or above it. And the conclusion that I think one can reach is that liquid water has the potential to be abundant on the planet as temperatures rise above melting. Let's look at what happens to the water and CO2. What's the volatile response? And I'm going to start on the left with the South Polar CO2 ice. That contains about 6 millibars equivalent of CO2. If you heat up the planet, that's all going to come into the atmosphere. This figure, the top one, shows where it's been detected in these colors. It's superimposed on a geologic map, and the bottom just shows where white ice is present. There's probably more CO2 buried here, but we don't have measurements right at the pole. It contains the equivalent of about 6 millibars. The second reservoir for CO2 that can be easily released into the atmosphere as adsorbed CO2 attached to individual regolith grains. My expectation is it has a few tens of millibars of CO2 present as adsorbed CO2. What's going to happen to it? This figure shows measurements of the amount of CO2 adsorbed at a temperature of 200 K. Obviously, temperatures will be warmer than that, but the key point of this is that at low saturations, most of the CO2 desorbs off the grains and goes into a gaseous phase. Relatively little is present as adsorbed CO2. At the high temperatures appropriate for release of CO2 and warmer sunlight, warmer sun, we're going to be very low. We're going to be at very low CO2 saturation. So most of the CO2 will be present within the atmosphere, and only a small amount will be present as absorbed CO2. That is, the warmer temperatures will force the CO2 out of the surface and into the atmosphere. If you add these up, it's maybe 50 millibars of CO2, and we can calculate the greenhouse warming that accompanies that. There's a lot of uncertainty. I think it's unlikely to be more than about 100 millibars, but the amount of greenhouse warming associated with 100 millibars is not that different from 50 millibars. For water ice over on the right, there's 20 to 30 meters global equivalent layer in the polar caps and the ground ice. We think that would be released. I don't show a figure of the adsorbed water, but if you have water at the surface as liquid, we're going to be near saturation rather than at low saturation. And that means most of the water present as adsorbed water will stay as adsorbed water. I've already discussed the possible deeply buried water within the crust. That can be up to about 1 kilometer of water ice. If that's present, it will move toward the surface, diffuse toward the surface in going from warmer buried temperatures to cooler surface temperatures, and could be released all the way up to the surface. Okay, what happens then? I've already mentioned the possibilities of an Eden-like planet or a dune-like planet. Let's go through these. First, a warm and wet Eden-like planet. Temperatures above the melting point, liquid water would be stable quasi-globally. We would expect there to be some sort of an atmospheric water cycle. And I think that one end-member scenario is having a very water-rich, liquid water-rich end state with abundant CO2. These conditions would be clement and very conducive to the presence of life, not necessarily an origin of life, but it would provide an environment in which life could thrive. Let's go to the other extreme. What happens to this CO2? Well, you have liquid water, you have CO2, maybe you form carbonates, and that could very effectively suck CO2 out of the atmosphere. The problem is that to form the carbonates, you need the cations like calcium, iron, etc. To form them. If you only have local water, like filling the pore space in the regolith, like water in a sponge, you don't have easy access to the type of weathering that would produce a lot of cations. On Earth, they are weathered out of rock and continents, and they flow to the oceans in rivers and streams where they get concentrated to the high abundance that would allow carbonates to form from the oceans. If you do form carbonates, though, the lack of plate tectonics on Mars would preclude easy recycling back into the atmosphere. So it's a one-directional removal. Water could hydrate minerals, or it could escape to space. At this end member, you would end up with a dry Mars where the water and CO2 have been removed from the atmosphere. And I think of this as a dune-like planet, if you're familiar with the movie or book Dune. Ultimately, though, I think we're unable to predict which of these end members would result or where in between, because we don't know enough about the nature of a water cycle, the nature of physical and chemical weathering in these types of environments to know what would happen to the water, what would happen to the CO2. Okay, that's enough for the sun. Can we terraform Mars more quickly? We're now going to get into what I think of as the fun part of the talk. People talk about terraforming it. Elon Musk has been the most vocal proponent of terraforming. This is a quote from him: "You need to live in a dome initially, but over time you could terraform Mars to look like Earth, and eventually you could walk around outside with anything on, without anything on." I presume he's thinking about spacesuits and not a Martian nudist colony, but with Elon, you can't really tell. Is it possible to terraform Mars? Can we do it using CO2 present on Mars already? Is there enough CO2 and can you mobilize it to put into the planet? Excuse me just a second here. Sorry about that. We've already gone through the sinks for CO2, and now we can look at them and ask, can we get the CO2 back? There's CO2 in the polar ice caps, 6 millibars. There's CO2 absorbed in the ground. Maybe there's 35 millibars. Maybe you can push it and get 100 millibars out. There's CO2 bearing minerals, carbonates. These are really hard to get the CO2 out, because you've got to heat the carbonates up to very high temperatures. And that would, to get a bar of CO2, for example, would require strip mining the whole planet. This is similar with adsorbed water. You'd have to heat the ground up, not as high as with carbonates, but you'd have to strip mine the entire surface in order to get that CO2 out. And with the adsorbed CO2, it would go right back in. So it's not going to be effective. Lost to space, you can't get it back. It's gone. And you could wait for continued volcanic outgassing to play a role here, but you're going to have to wait 1 billion years. And even then, you're not going to get more than a few hundred millibars of CO2. So can Mars be terraformed? You know, not with indigenous CO2. I think that's unlikely to happen. But there is an out here, and that is you can create very efficient greenhouse molecules artificially. Think of it as things like chlorofluorocarbons that have been selected specifically to be more effective greenhouse gases. People have actually worked on this and identified them. The possibility then is there for CO2, for chlorofluorocarbons to be a very effective greenhouse gas, but it would require significant manufacturing capability, more than we have on Earth for chlorofluorocarbons. And, you know, gee, we haven't even sent a person to Mars. So imagining a manufacturing capability that could do this would be very far into the future. So I've got one last topic that's going to devolve into 2 topics, and that's, where are we going with Mars exploration? What does the future hold in store? I think the science objectives for Mars are very well understood, and I'm not going to go through these in detail, but the questions about life, the history of climate and volatiles, and the geology, geophysics, geochemistry of the planet, that is, the evolution of the planet as a planet. If we look at searching for life, we've determined that it's not easy. Viking and the Mars meteorite Allen Hills 84001 were the 2 best opportunities we had for searching for life. We did not find anything, and we came up with, at best, ambiguous results that do not preclude life, but do not support its presence. We haven't seen anything in subsequent analyses, for example, with the SAM instrument on Curiosity or with Trace Gas Orbiter. I think people are coming to the consensus that answering the question for life is going to require going to places where liquid water was present, collecting samples that might retain a remnant of life had it been present, and bringing them back to Earth to study in the laboratories here. We can do a lot more in the labs here on Earth than we could do with even a full range of robotic spacecraft. So where are we on this? I think everyone knows that samples are being collected by the Perseverance rover in Jezero crater. Jezero is the site of an ancient lake filling the crater. I'm going to show what's in the red box in the next chart, which shows where water flowed into the crater and produced this nice delta deposit as it hit a lake and deposited its load of sediment. Perseverance has been tootling around here. I'm not going to try to trace out its path, but it's collected a couple of dozen samples to date, and we're holding those to return to the Earth. The architecture for return is currently under development, and samples are planned to be returned sometime. NASA's in the middle of revamping the planned architecture, so I can't tell you when that will happen, but it will happen. Finally, I want to say just a word about human missions to Mars. And I want to say this because even though human missions to Mars have been part of NASA's plan for a while, they were highlighted in President Trump's inauguration speech. He said, "We'll pursue our manifest destiny into the stars, launching American astronauts to plant the stars and stripes on Mars." I think this got the attention of a lot of people in our community, and I've written down some of the questions that have come up about his thinking and about the plans. And right now we've heard very, very little. So these are questions rather than answers. For example, does Trump, in making the statement, does he imagine that we will have a human landing during his 4-year term? I can't imagine that would be realistic for a number of reasons, not least of which is we are woefully ill-prepared at this point in terms of the hardware and mission concept. We don't know what architecture we would use. There's a whole host of technical issues that would need to be resolved. Working in the zero-G environment and low-G environment on the surface is not easy. I don't know whether Trump envisions a flags and footprints approach or a significant program of human missions. That is it going to be a one-off mission to go there and say we've done it? Or are we going to develop a sustainable program? Does this mean that we will reinvigorate the Mars robotic program in support of human missions? If we emphasize Mars, are we going to cancel the Artemis program to the moon? And intertwined in all of this, what's the role of commercial entities, in particular SpaceX? And these are questions. On the left are 3 different architectures that have been proposed. I'm not going to go through them. This is my last chart. I think Mars is a compelling target, both for getting people excited about science, excited about the planet, and for science. Mars is particularly compelling for understanding how planets work, how life might interact with its planetary environment, and whether there could be life on Mars today, and if there is, or if there isn't, what it tells us about the potential for life in the universe. This was going to be my last chart, but I've got one more that I'm going to show just because I didn't delete it. And I've got to go ahead a few. To paraphrase other people on that same point, going back to Arnold Schwarzenegger in Total Recall, with a phrase that Buzz Aldrin has picked up, "Get your ass to Mars." And at that, I will stop here. I'm going to stop my laser pointer. How do I do that? I'm working on it. Give me a second. And let me stop sharing. And again, I will just say thank you for the invitation. This has been a delight to give this talk, and I would be pleased to answer any questions or engage in discussion.
Thank you, Bruce.
I'm not going to monitor who's asking questions. I'm going to let people just speak up or ask Mike if you would monitor them and call on people. Force you to do some work.
Donnie's in charge of this session, but I have my hand up, so let me just ask
Yeah,
a quick question.
Go ahead, Mike.
One of the big uncertainties you had was in the crustal water amounts. So what's it going to take for us to constrain that? What kind of future mission could tell us how much is there, or is it not possible? What do you think?
You know, if we drill down, we're going to hit ice. We know that ice is there near the surface. We know in the mid-latitudes it extends to at least a couple of 100 meters depth. That ice is going to be mobilizable, but 100 meters of ice at the mid-latitudes, given the spatial extent, translates into less than a few meters globally as a global equivalent layer. So it's not a major perturbation to our understanding. If we want to get deeper than that, I don't imagine we're going to be able to drill down. I really like the seismic approach that Wright et al. Used. I just don't think that the data had the quality to support it. I think it could be done with better seismic data or with localized seismic analysis. You know, putting geophones down and triggering small explosions to explore the down to several kilometers depth. That's the volume we're talking about. Either one of these is very doable, and I would sure love to see somebody try to propose something like that. It could also be done using electromagnetic techniques because water as an electrical conductor would manifest itself if you have EM sounding. That can be done with the rover just putting a magnetic coil spread out over a few hundred meters or a kilometer on the surface. We have the technology to do any of these today. It's just a question of what the implementation would look like and the priorities relative to other scientific goals.
Yeah, just if I could just add to that quickly, we did all of that with Apollo. Okay, Apollo did active, passive seismic, and also electromagnetic sounding. So the technology's there, and the ability to get it off planet is also there. So I think those are the main things, as you point out, Bruce. Excellent talk, by the way.
Oh, thank you.
Thanks, Bruce, and thanks for that backup, Jim.
Chris, you got your hand up. Go ahead.
Bruce, thanks for the good talk. I just want, so you could squeeze it if you warmed up Mars a little bit. I understood the slide. You could squeeze out maybe 6 millibars of CO2 from the ice cap. Is there any significance to the fact that Mars straddles? So it's like 6 millibars or so. And of course, the triple point pressure is slightly above or something like that. So if you doubled the atmospheric pressure, it could still be unstable to evaporation if the partial pressure is lower. But if the total pressure, so it could be stable against boiling at least. So can you have like transient puddles just by like doubling the atmospheric pressure that can end up being important for things?
There are two questions in there, and I'm going to answer the one you didn't ask first, and then the one you did ask. And that is there any significance to the atmospheric pressure today being 6 millibars? For example, a number of decades ago, Ralph Kahn proposed that that was not coincidence, that the presence of liquid water allowed carbonate formation until the pressure dropped to the point that you couldn't get liquid water, and then it stopped at 6 millibars. I don't think that's the case. And the reason is there are other sinks for CO2, like adsorbed CO2 in the regolith, and the surface isn't a uniform sphere at 6 millibars. You have temperature pressures ranging from about 15 millibars at the bottom of Hellas or Valles Marineris, up to half a millibar at the top of the Tharsis volcanoes. So it's hard to say 6 millibars. You have a wide range spanning more than an order of magnitude. So I don't know what the significance there is. In terms of 6 millibars being the triple point of water, 6.1 millibars, and whether that would mark a transition from sublimation of water ice at the surface to boiling of liquid water, that's a smooth transition. And I don't think it's significant. You don't see a dramatic increase in the water loss rate at 6.1 millibars. You see the same exponential increase with temperature, but a transition from one process to another process. So my gut sense is it's not going to make a big difference.
Interesting.
I will say I haven't backed that up with quantitative numerical models. And since I'm halfway to retirement, somebody else can do that. Jim, you've got a couple more decades in you before you retire. You can take that one on.
Yeah, we've actually done some. Yeah, I think there's a paper by Roger Phillips, et cetera, about the doubling of the atmosphere and recent obliquity changes where it mobilizes CO2 in the south polar cap. And that's a good reference for, and the effects are, well, you increase atmospheric pressure, but I don't think it pushes it over. The question was, does it explain the gullies? For example, a quick transient, if there's surface ice and under the right inclination, under the right orientation positions of where surface water is, snow and ice are sequestered, it could make a difference. It's right on the margins, I think.
Jim, you remind me of something that I should have mentioned, and that is the role of obliquity. The obliquity today is 25 degrees. That's the tilt of the polar axis with respect to the normal to the orbital plane. And it's thought to wander between about 0 and 70 degrees. And the modal value statistically in the distribution is above 40 degrees. At that tilt, all that CO2 in the polar ice would be in the atmosphere. So you'd have a pressure of 12 millibars. And that's a much more likely value than the 6 millibars. So I think as a causal mechanism for why it's 6 millibars, I think that sort of takes that out of the game. I think it's just coincidence.
Yeah, I'd agree with that. And I think we're living in an anomalous time on Mars right now. I mean, it's not your average, as you point out there. So that's something to keep in mind as well. I think it underlines your point about whether 6 millibars is a terminal point or some significant evolutionary stop, if you will, for a while. I don't think that's well founded by that other evidence. The other thing to think about is also the obliquity often goes below about 15 degrees. And in that case, the CO2 condenses out at the polar caps, and you end up with essentially no atmosphere to impede incoming meteorites, et cetera. I don't know what Elon Musk plans to do about that. Probably just take a chance it won't happen during his watch, but we'll see. But that's an important thing. And we actually see evidence for CO2 glaciers in the high latitudes of the north polar regions. It's really amazing. I mean, these very distinctive lobate flows that signal both in their position of accumulation and also in their flow morphology a very a rheological property of CO2 rather than water ice. So that's another thing to think about in the history of Mars.
And I'll just say, sort of summing it all up, I think these uncertainties really underlie what some of the major questions about Mars are, trying to understand the history of volatiles, the geological history, how they couple together, and the relevance to possible life. And to my mind, that justifies a vigorous robotic program of exploring Mars, and it justifies sending humans to Mars to carry out exploration that we just can't do robotically.
Can I ask another?
Just to be
No,
quickly
go ahead, Jim.
kind.
Sorry.
Yeah, no. I was just going to add that Bruce, in all his modesty, he would not mention that he was chairing a committee that I was lucky enough to serve on, which talked about future human exploration of Mars. And I think, some really, really good reasons and good strategies. Years ago, when NASA had another epiphany that we want to send humans to Mars around the turn of the millennium, I guess, this millennium, we were tasked to do design reference missions, and we did 40 different areas that were very compelling in terms of Mars human design reference missions. So there's a lot of activity that's already occurred, a lot of good thinking going on now, and I think Bruce, you might want to put into chat or send around your report, because I think it's really compelling.
Thanks, Jim. And I'm just hoping that we'll be able to send humans to Mars before the turn of the next millennium.
We can hope. Let me ask a naive question, Bruce. So, as Jim knows, one of the big problems with Venus today, for example, with the idea of a wetter earlier history, is there's no oxygen in the atmosphere, right? It's very hard to get oxygen out of Venus because of the gravity well and other things. So, I mean, I don't think it's the same, but there must be similar things going on with Mars. It is a much heavier, molecule, O2. So, do you see that playing any role here in that, it's not hard to get the hydrogen out. We all know that. Those escape rates are very well measured, but the O2 is a little bit tougher. And I'm wondering, there must be still some around. I mean, we know that surface is oxidized, but it can't all be sitting there, right? So what do you have to say about that?
It's not that hard to get rid of oxygen. Yes, it can go down into the crust and oxidize surface materials, but there are mechanisms by which it can be lost to space. I mentioned dissociative recombination as an example, and that is capable of removing as much oxygen as you want that would be released from water. I can quantify that, but I'll just leave it at that for now. The biggest uncertainty is whether oxygen that is lost to either up to space or down into the crust comes from water or from CO2. So, because there are mechanisms of removing it either way. So the coupling between water and CO2 in terms of integrated loss to space and integrated history is one of the biggest puzzles I'm struggling with right now, and there isn't a good answer. We need more data and better data.
So what kind of data do you need exactly?
Samples from different ages, unadulterated samples from different ages that can be used to infer the history of D2H, the history of C1312, the history of O1816. That would be the single biggest thing I'd like to see.
Yeah, but I mean, I remember your paper from a couple of years ago, and you say unadulterated D2H, but the ranges of D2H as any given sample are huge. So what do you mean unadulterated? You're always going to have this problem.
When I said unadulterated, I meant going to Mars, picking up the samples and bringing them back, rather than relying on samples that have been ejected by impact. There is the problem of the wide range of D2H. We think that results from exchange of water between the rock and the ambient environment through history. So you can't, from one rock with a wide range of D2H, you can't infer what the D2H was at the time the rock formed. It's a complex geological problem. We've sort of solved that on Earth. We know how to deal with that, but we don't have the samples yet to allow us to do it for Mars. Human missions.
Okay, sell that.
Mike,
Thank you.
Mike, if you asked me that question, I would say what I would want to see is a time machine to go back and make the measurements and check it out.
Well, we may have that
like
before we have
answer.
human missions.
That's true.
Yes, maybe you're right.
Well, we're running out of time. Go ahead, Igor, and
yeah,
ask.
I just have a short follow-up question to Triple Point. So if we are talking about obliquity changes, those were happening relatively recently. So then that means that the atmosphere was thicker than Triple Point, and also it was slightly warmer. So is there any evidence of liquid water actually recently being present on Mars? I'm not talking like real lakes, but some parts, like some minerals formed like at the equator, or some soil water movement. I don't know.
The actual evidence that points to liquid water, I think, stops in the range of 1 to 3 billion years ago, and it's minerals that require liquid water that are dated at those ages. I can infer the presence of liquid water more recently, but it requires things like looking at the history of volcanism, which certainly would have released water and would have involved at least transient liquid water. And that would have occurred as recently as the last couple of million years. So I'm not aware, I'm going to get in trouble because I'm going to point to Jim in a second. I'm not aware of other evidence for liquid water within the last couple of billion years. Jim, do you have anything in mind?
Yeah, I would say the gullies. The gullies are the key piece of evidence. We had a paper in Science 2 years ago, maybe, which described the conditions under which they might have occurred. So those are in the order of hundreds of thousands of years, probably, maybe a million or so. So these are inside craters typically, and they essentially are things that run downhill. They're transient, and we put together a set of climate models that would suggest maybe what the conditions were at the time, and we trace them back. So I'll send that out. It's a science paper. It's Dixon et al. I'll send a link to that to Mike. Okay.
I don't.
Thanks, Jim.
With all due respect, I don't think there's a consensus yet that those are water-related features.
That's true.
I tend to lean toward the water explanation, but I don't see a consensus yet.
Yeah, what we showed actually was that there was a bimodal characterization. You can actually see small landslides, et cetera, that occur when the CO2 becomes mobilized. Okay, so that the temperature distribution is such that the CO2 that's partly buried by soil undergoes evaporation, and it causes downslope movement of materials. So that's one mechanism, and Forget et al. Has shown, I think, that's quite likely. On the other hand, there are times when the triple point is exceeded, and you can get these conditions under which you also get liquid flow. So we weren't saying that's the only way to do it. We were saying there's a couple of models and more investigations in terms of the temporal distribution. Hopefully we'll slide into one of those periods soon on Mars. So
fair enough.
And we can predict when that's going to be based on Lascar's work.
Awesome.
Thank you. Yeah.
Thank you so much, Bruce. And thanks for dialing in, Jim. Great to hear you.
And thank you for the invitation. It's a real pleasure to have been able to give this talk.
Thank you. It's really great.
Yeah, this was great. Thank you.
Thank you, Bruce.
Thanks, Bruce.
You're welcome. I'm going to leave the meeting now. Thanks.
Okay.
All right.
Take care.
Have a good one, everyone.
Bye.
Yeah.